Hello, my name is June, and today I want to talk about different models for AI generated art. AI generated art has, in recent years, come to light and gained a lot of attention due to its ability to create art from simple text prompts. There are many different techniques, each with their own strengths and weaknesses, but today I'll be focusing on two of the more popular methods: generative adversarial networks and diffusion models. I'll be talking about how these models work, their strengths, and their limitations they face, and try not to be boring. The first model I want to talk about is the generative adversarial networks, or GANs for short. GANs was first introduced in 2014 and was one of the first deep neural networks capable of learning an image. A GAN consists of two neural networks that are in constant competition, the generator and the discriminator. The generator's job is to create fake data, an image, while the discriminator's role is to evaluate whether the data or the image is real or fake. It's like a game of cat and mouse where the generator wants to fool the discriminator and the discriminator wants to catch the generator in the act. Together, this pushes the generator to improve and produce data that becomes indistinguishable to the discriminator. And here's the math of it. The generator starts with a random noise vector z. It generates an image, gz, which it sends to the discriminator. The discriminator evaluates two types of inputs: real data from the dataset and fake data from the generator. The real data is denoted by x. The generator aims to minimize the second term here, log of 1 minus d of g of z, trying to fool the discriminator into thinking its outputs are real. Meanwhile, the discriminator works to maximize both terms, correctly classifying real from the fake. And together they solve the minimax optimization problem. Training GANs is an iterative process where the discriminator provides constant feedback, helping the generator refine its approach, and eventually the generator output becomes so real that the discriminator can't really tell the real thing from the fake. But GANs aren't without their challenges. They often suffer from something called a mode collapse, where the generator produces only a limited range of outputs instead of exploring the full diversity of the dataset. Mode collapses happen when the generator starts producing only a small number of patterns that trick the discriminator. It gets stuck focusing on just a few main features in the training dataset, and it misses out on the full variety of patterns that should really be there. And this is where diffusion models come in. Diffusion models, instead of trying to trick a discriminator like the GANs do, work by gradually adding noise to an image and then learning how to reverse that process. I'm going to dive into how this process works and why it can produce more diverse and potentially stable results. The diffusion model has two main steps. The first step is called the forward diffusion process, where an image is transformed into random noise, and the second step is called the reverse denoising process, where the noise is converted back to an actual image. The forward diffusion process starts off by generating a simple random sample. From there, the model gradually adds more and more noise in small steps using a Markov chain of capital T steps. It's like layering static over an image. Each step makes the original picture, the original data, a bit harder to recognize. In the equation, x sub 0 is the real data, the image. We take the current version of the data, which is denoted by x sub t minus 1, and add some noise with variance beta sub t. This makes x sub t. The variance parameter beta sub t can be fixed, or it can be a schedule over the capital T number of iterations. Variance schedule can be linear, it can be quadratic or cosine, etc. The image here compares the linear and cosine variance schedules. And by the time the process is finished, the sample has changed into something that matches the level of randomness seen in actual real-life complex data. The purpose of the process is to teach the diffusion model how to quote-unquote mess up simple data in a way that mimics real-world complexity. Now on to the reverse process. The reverse process is what sets diffusion models apart from the other models, like GANs. Instead of generating data all at once, diffusion models work by reversing the noise adding process. During training, the neural network learns to recognize the specific noise patterns added at each step and figures out how to remove them. At the final step of the forward process, when t gets very large or when it approaches infinity, the variable except capital T behaves like an isotropic Gaussian distribution, meaning it behaves like a normal distribution. If the model learned the probability of x sub t minus 1 given x sub t, it can take this random noise from a normal distribution, step backwards through the process, and gradually remove the noise. Let's assume that the reverse process follows the Gaussian distribution and that we use a small enough variance beta. With this, we set our model p sub theta to also be Gaussian, but we also just have to adjust the mean and how spread out the data is. If we keep applying the reverse formula for each step, or what we call the trajectory, we can gradually trace our way back to the original data. And by doing this for every step, the model learns to predict things like the average values and how spread out the data is at each point of the process. So how do diffusion models actually generate art? Tools and applications that utilize diffusion models start with a random noise vector and refine it into an image that fits what the user wants. For example, if the prompt is a forest at sunrise, the model begins with just pure noise and gradually, step by step, adds elements like trees, sunlight, until the image is what the user wants. To wrap things up, both GAN and diffusion models have really shaped the world of AI-generated art. GANs are great at creating realistic images, but they do tend to get stuck and make only a limited range of outputs. Diffusion models, on the other hand, offer more stability and flexibility, but they are a bit more demanding in terms of computing power. As AI keeps advancing, there are more and more AI models that help the creative community. Well, that's it. Thank you for listening, and I hope I made some sense today, and hopefully you learned something that you didn't know 5 minutes ago.